Hello, my name is Tyler Hamilton, and this is my final presentation for CEE 485. I will be showing how I use the systems model approach to optimize a water distribution network. This project is based on my senior capstone, where my team designed the infrastructure for a 487-acre master plan community in Apache Junction, Arizona. Across Arizona, urban expansion is rapidly increasing the demand for new infrastructure. In areas where large master plan communities are being developed, civil engineers must design water distribution systems that are both cost-effective and hydrologically reliable. These systems often span hundreds of acres and include dozens of pipe segments, each with unique flow and pressure requirements. In these developments, engineers must consider economic constraints while still meeting regulatory standards for pressure, flow, and system performance. The problem is designing water distribution systems for growing suburban communities often leads to oversized or inefficient pipe networks that are unnecessarily expensive and may not meet hydrologic standards. The objective of this water distribution system is to minimize the total cost of the water distribution network while ensuring all pipes meet hydraulic performance criteria. This includes the cost of every pipe in the system based on its length and the unit cost per foot of the material and diameter selected. While cost is the primary goal, the system must also meet strict hydraulic standards, including limits on flow velocity and head loss, to ensure that water can be reliably delivered throughout the development. The model uses Excel solver to select pipe options that result in the lowest total cost, while still satisfying all technical and regulatory requirements. In this system, the design variable is not pipe diameter. Many people would be quick to make diameter the design variable. However, if we are optimizing cost, the cost of the material is the most important variable. Therefore, the design variable is a combination of the diameter and the material type. Taking a look at this table, the cost of a pipe relies on the size and the type of material being used. To model this in Excel, the program can be assigned the variable cells a whole number 1 through 24, which in turn assigns the diameter, cost, and the Hazen-Williams friction coefficient. This is easily scalable, as you can add more materials to test by continuing this chart, increasing the variable cell bounds. For this system, material type number is the design variable. The system has three types of constraints. First, parameter constraints. These constraints are predetermined, some by the variable cells and others by outside sources. The friction factor and diameter sizes are determined by the Excel solver function and are subject to change. The pipe lengths and flow requirements are fixed. As Excel is limited to optimization and can't directly model water distribution systems, the flow values come from the program EPANet, which specializes in simulating hydraulic networks but not cost optimizing. Secondly, the balance constraint of mass balance must be satisfied where inflow and outflow at junctions must be equal. Third, the inequality constraints include limits on velocity and head loss. Velocity must stay between 2 and 8 feet per second, and head loss below 10 feet per 1,000 feet of pipe. These constraints combine to influence the Hazen-Williams formula for head loss. The objective function calculates the total cost of the system by summing the cost of each pipe segment. Cost is determined by multiplying the length of each pipe by its unit cost per foot, which depends on the pipe's diameter and material. While material type is a design variable chosen by solver, it doesn't appear directly in the equation. Instead, it determines the cost, diameter, and C values that are applied from the table. The model uses the Hazen-Williams equation to evaluate each pipeline's head loss and velocity, ensuring that all parameters stay within acceptable limits. To reiterate, the cost for each individual pipe segment is tied to the material and size selected by Excel solver. The best solution is the lowest cost combination that still satisfies all hydraulic constraints. This helps us avoid overdesign, reduces unnecessary expense, and results in a system that is both efficient and affordable. Thank you for your time.